So I'm Andrew Strudwick, so I'm actually going to talk through kind of some of the activities and capabilities we have in two lab areas. So that is our deposition and printing lab facilities. And then some work we've been doing around sustainable practices and kind of projects we're working on with kind of net zero gains or objectives. So that's a summary. Same again. So if we start with the deposition lab. So mainly in the deposition lab, we work on CVD-based processes. So this is taking typically gas precursors. We do have some metal organic CVD work taking place as well. And then using an energy source, be it typically thermal energy through heating, or we do have plasma technologies as well to crack some of the precursors with plasmas. And then depositing those graphenes or other 2D materials onto target substrates. I'll go through in a bit more detail what we can target with the different pieces of equipment we've got. But primarily we're doing that to then try and integrate those materials into applications and end uses. So our first system is a batch CVD system where we can produce kind of 10 by 10 centimeter scale graphene on either copper for single layer or multi-layers we can grow on nickel. And these give us a basis for kind of tweaking growth parameters to try and optimize performance. And we use those kind of 10 by 10 centimeter pieces to start kind of proving or doing proof of concept experiments and projects with companies in a range of different application areas. So we've done things on GFETs for sensor applications. A lot of the work, which I wouldn't have imagined kind of 5 years ago, has moved into an area which Nick mentioned, which is improving kind of crossover and barrier membranes in energy applications. The bottom one as well is another energy application, so kind of hydrogen generation in MEAs and PEMs. Graphene has a role as a selective filter effectively for hydrogen and protons. We then have a roll-to-roll system, which uses very much the same kind of physics and chemistry as the process in the batch system. But here we can produce materials continuously. So rather than it being kind of a 10 by 10 centimeter piece, which typically takes 3 hours to produce, we can kind of run the machine with its 15 centimeter wide foils continuously, typically at a kind of 4 to 5 meter per hour rate. So you're looking at like over 100 times scale up of the process. Some of our projects now that are entering a set, well, most of them have entered a phase 2 and are looking at a phase 3. We are getting to the maturity level where these technologies are becoming applicable. So the need for graphene on this scale is now needed. I'll touch upon some work we're doing with a partner as well on associated technologies with this, because growing the graphene on the metal is one thing. You need the ability to get the graphene from that metal onto target substrates where you might want to make devices or generate applications with it. Another piece of work we're doing with one of our partners, NPL, who are obviously running a session next door, is developing QC tools. So one of the QC tools we're working on is inline Raman. So we've actually ran CVD processes on the roll-to-roll with a Raman system probe over one of the rollers, and as we change the parameters on the CVD growth, you can see the characteristic changes in the Raman signal, and use that as an indicator as to how your growth is performing on the surface. The third system we have is slightly different. So Simon from Paragraph earlier on mentioned MO CVD, so that's using metal organic precursors. We can't grow graphene here with that technology. That's something Paragraph have cracked. But we can use MO CVD systems for targeting other 2D materials. So to date, we've produced tungsten disulfide and molybdenum disulfide, which are both semiconducting materials. And we can produce those directly on wafers and then go and take them over to the NGI for kind of post-processing into electronic devices, or we can kind of form membranes with those systems too, depending on what the application area is. There is scope in the system to do some boron nitride work as well. We're just waiting for the right project to come along to change the precursors and push a project on that front. So the good thing about the MOCVD system we have here is it's made by Astron, who make a lot of these systems that are widely used in industry already in kind of semiconductor fabs. So it's industry-ready technology. It has kind of the gas control and the precursor control that you need. So when we develop a process here, it's much closer to being able to translate into an industrial setting compared to a lot of other research on the CVD growth of TMDs in particular are still using tube furnaces and kind of solid precursors, which translational into industry, it's quite a large step to then take those parameters and try and do it at scale. We also have, within kind of the deposition capabilities and the wider capabilities of the building, we have a small clean room here where we can do some quick trials on kind of transfer processes, trying to get the materials that we produce onto devices or onto substrates for kind of wear testing or optical testing or sheet resistance measurements. But we also, like I say, have access into the wider university facilities, in particular facilities at the NGI, where we can do proper kind of e-beam or photolithography to produce devices out of these materials if needed. So these just some ideas of potential projects that we're interested in the CVD space. If anyone else is interested in looking at any of these areas, then give us a shout. We're very keen to drive some of the scale-up activities on CVD. And like I say, we are looking to kind of build the supply chain on that front as well. We can bring two partners together where we don't want to be a production house, but if a company if we can make those links to build a supply chain, then that's something we're very keen to do. Anything on the MOCVD side as well, any novel devices that people would like to look at, we can kind of produce the material on the wafer to start to make that a reality. And then there's a bit on novel transfer techniques, and again, that will tie into a little bit on partner companies and how they're working in that field to drive the technologies. So we recently, I don't know, 6 months ago, started the Associate Technology Partnership way of interacting with the GEIC. So the idea is to take technologies that companies have that we see as beneficial to increasing the market size or enabling a new technology area that's previously not been able to be exploited with 2D materials, and to work together to kind of mutually benefit and push the market forward. So our first, and Morton's in from there he is 2D technologies, which have worked to develop basically a graphene transfer platform, which is going to simplify how companies can kind of use graphene, CVD graphene in particular, in a kind of more simple, flexible way to start really looking at doing proof of concept, proof of principle testing on application areas that might be of interest to them. The transfer of CVD material from the metallic substrates has been a big challenge for a long time. Kind of companies have been working on this for kind of 10 plus years. So we see this as a real enabler now to help us progress along those lines. So now I'll move on to the printing lab. So in the printing lab, we kind of work on things in a slightly different way. So deposition lab, we're making things from the gas phase. In the printing lab, we are typically formulating inks and slurries from kind of bulk 2D material, well, as bulk as 2D materials come, but kind of platelet materials, and then formulating with binders and surfactants to keep them in suspension, inks, which we can then process on our equipment to form kind of device structures or things like strain gauges, or we've done printed heaters and things along those lines recently. The good thing in the printing lab is we can kind of approach things at multiple different scales. So kind of our main workhorse in there is probably the screen printer, where we can produce kind of 25 sensors in a single print. Very good for kind of prototyping if a technology is working, so we can generate statistical data pretty quick. The design of the screens is relatively simple, and we can get those turned around within a week or so with one of our partners that we work with. And it just gives you a flexibility to try something. If you've got an idea for a device, you can trial it. We typically can run packages where we then optimize those designs, go make a second stage screen, and then go again. And yeah, it's really handy, flexible system for trying those processes. I think there's a little video there of one of the prints going out. So there's some strain gauges, pretty much, that you can then go and incorporate onto a fabric or into a composite for measuring strains. These are kind of the space that we operate in the printing lab. So we cover quite a wide range of sizes and resolutions and kind of speeds of printing. If you've done a proof of principle on the screen printer, you then often want to, a bit like in the CVD lab, we then might want to push that into a continuous process. We have a roll-to-roll called Teamer base coater for that purpose. So once you've done your proof of principle on the back scale, you can then design a screen where you can take that forward. And again, we're not aiming to be a production house. This is very much like a pilot scale facility. What we tend to do with the base coater is de-risk activities for companies. So a company will come to us with either a new substrate, a new formulation, or a new design that they're not sure they can print via these methods, and we will do the first stage with them before they then approach a full production site. We're a good stepping stone to just de-risk that final production activity for them, so they can do the trials with us, get a set of parameters and a set of materials that they know or have much more confidence are going to work, rather than going straight to production and potentially having a failure that's costing them a lot of money in materials and time. Here's just an example of some biosensors we've printed. So these are, it's a uric acid sensor in this case, but these are typical structures you get for like glucose sensing and similar. So again, just an example of kind of the amount we can print using the screen printer in a single run. You can then test, like I say, 2,500 sensors all within a quick turnaround. Here's a little bit again on some of the printed heaters we've done. So you can see thermal imaging at the bottom, looking at the heat being generated as we pass the current through it's actually silver contacts, and then the graphene's acting as a spreader in the middle to spread that thermal heat. Again, there's just an example of a lot of areas we can carry out sensing projects in. So humidity, some bio stuff, temperature. We've covered quite a range so far. Then to move on to some of the other aspects of what I'm going to talk about. So sustainability is a big thing for the facility in general. In the printing lab, we're especially keen on it. We've driven some of the activities here on that side of things. Printed electronics in general offers kind of more sustainable routes than some traditional electronics. Basically improving the recyclability of the materials. We're very keen within projects, if companies are currently using hazardous materials or solvents within their production methods, we're keen to explore ways of making that chemistry more greener in kind of the first parts of packages. We're also always looking at ways in which we can recycle our substrates or use already recycled substrates for testing. Again, just to drop the footprint on the effects we're having. Again, linked to some of the work we're looking at with 2D technologies on dry transfer. Kind of one of the main issues with the CVD processing when you do it at scale is once you transfer off the graphene, off the metal, if you do that using the traditional kind of wet chemical ways, the generation and the disposal of the etchant and the materials within the etchant, and also the amount of waste copper that you end up going through during that processing, or nickel if you're doing multi-layers. Number one, it's a very high cost, and number two, it's very hard to get rid of the waste. So anything we can do on that, where we can either reuse the metal substrates, we're very keen to push to. We've also started working with the wider university. Again, this is a benefit of being where we are, to start to tap into their expertise on life cycle analysis. So we've worked with partners to start looking at life cycle analysis of their processes. And again, being linked with the university, they have a lot of expertise in that area. They have access to the databases that you need access to start looking at these things. So that's, again, kind of a service we can tap into if it's of interest. Again, at the bottom, again, for the wider facility as a whole, we have undergone kind of an evaluation under the LEAF Lab Sustainability Scheme, which is kind of a measure on how sustainable your labs are, and all the labs here are rated at silver at the moment, and we're just waiting for an audit to push for further accreditation on that front. But again, it is a key driver for us. And then on the work we're doing kind of on net zero projects. So the main ones are around sensing of gases. So I don't know if anyone met Ava yesterday at the NGI, but she got a company called Perfect Sense, and their aim is to kind of be able to monitor people's exposure to kind of pollution or harmful gases, and track that exposure with precise location data, so you can start to generate data centers or data collections on hotspots of pollution, and then you can look to reduce those. So that's something we're working with them on. We have a Swedish company working with us, Hydrogen King, who are looking at kind of solid oxide fuel cells for hydrogen generation. So that's using capabilities in the printing lab to help solve some of the issues they're having around electrodes and integrating the solid oxide fuel cells within their systems. We're also working with a company based just outside Nottingham, Absorption, again on kind of graphene as an improver for membranes. This time it's in an electrolysis system. It's actually not for hydrogen generation per se, although it will lead to improvements on that front. It's actually for isotope separation, which is key enabler for some of the new fusion technologies, and for dealing with some of the waste of current nuclear technologies. So that's the end of my talk. So, like I say, we have a lot of equipment, but most importantly, we do have a lot of expertise. The equipment's fine, but it's the team that delivers the results. And I think that's where we add the most value. So if you are interested in working on any of the areas I've mentioned, then just give us a shout, and we'll see what we can do.
All right. Thank you, Andrew.